Hey everyone, I was going to do a quick integration by parts tutorial. I don't really have much of a board with me right now, and I just wanted to get it started here. So I'm going to show you some of the basics here. All integration by parts is you're running the product rule, which you learned in Cal 1 in reverse. If you shift this piece over there, it's opposite because it's hard to, yeah, if you just algebraically manipulate that and then differentiate both sides, you will have the product rule basically. Um, Integration by parts is used if you have two terms that are multiplied together, and especially when I say one can be simplified here, I mean one can be one of those terms can be integrated or differentiated into a term that's a lot easier. And I will show you, you're going to integrate one, as you see here, and differentiate the other. And I'll show you here what I mean by that and what you'll be doing here. It can really help to know which term to integrate and which is the best to integrate and which is the worst. Of course, the worst to integrate is obviously the best to set as your u, and then you make it into a du and differentiate it. And that's the best for your v, so you don't want to make that your u. Just remember the word ilate right here. So if you see an inverse function and you need to integrate by parts, you want to differentiate that. Something such as arctangent x is a good thing to differentiate. Logarithms are usually pretty good to differentiate. As for algebraic functions, they're pretty they're usually good to differentiate because they go away pretty quickly if you differentiate them. And the trigonometric is it's okay to integrate because it doesn't get any nastier. It just stays the same, as does the exponential. So those two right here are good choices to integrate whenever you can, because they don't really, or sometimes they are. Sometimes they can't be, because you can't integrate some functions like x tangent x. It has no closed form solution, as some of these integrals don't have a solution. But the best way is to get those two is, you know, to integrate. If you have something, integrate one of those two and then differentiate. You usually want to differentiate those three. So here I'm going to do a real basic example. Let's make sure y'all can see it. I don't really know if y'all really care to see my face or anything, but here, x cosine x. It's a relatively easy function to integrate, and let's make sure. Okay, good. So here we have to select our u. Here's what I like to do. U, well, you select your du. So u, du, v, dv, like that. Okay, so the first thing you do is you select your, we know that because of ilate, cosine x is good to integrate. It's the best to integrate. It's better than algebraic, so we're going to integrate cosine x. If I can, yeah. And that means we're going to differentiate x, which goes to dx. Cosine x goes to sine x. So you get x, and we're just running the product rule in reverse. X sine x uv minus integral v du, which is sine x. So you get, that becomes negative cosine of x. So what you're going to get is x sine x plus cosine x plus, of course, your integration constant, as you see. And after that, you're done. So you're going to see that's the final solution. Okay, here's one a lot of people won't really see off the bat and what you're going to actually do. What you want to start with is actually parts. You could technically look it up in the back of your textbook or whatever, but if a teacher asks you to do it on the test or something, you're probably going to have to show your work. So a lot of these, of course, we see that we have an arc tangent right there. So it's a pretty bad choice to integrate, because of course, well, what's the point in integrating it if we don't know how to integrate it? So what we're going to do here is let u equal arc tangent x, and then dv equal dx. So v equals x, and then du equals 1 over x squared plus 1. Okay? Now that we've established that, we just do our usual formula. The x arc tangent x minus integral of x over x squared plus 1. Okay, so now we see this right here. Now that this should just be a usual u substitution, nothing much to it. So we'll say u x squared plus 1 du equals 2x, so 1 over 2, just integrate 1 over 2u du, and after you have that, excuse me, yeah, 1 over 2u, that's right, you're going to get out 1 over 2, you get the natural log, the absolute value of u, 2, so then you just sub back, and then our solution, I'll write it right here in this little box. It's going to be x arc tangent of x minus ln x absolute value of x squared plus 1 over 2 plus c. That's it. That's what you have to do there, and you have to remember on ones like this that you have to integrate your dx into an x, which can sometimes be a bit difficult to see, but on terms like this, you have to know that's how you do it. Okay, here's one that's a bit trickier. It has a nifty little trick. You'll see this one a lot, and this is another thing you'll have to know how to do when you look at integration by parts. So we'll go ahead and get started here. We'll set up our u, du, v, and dv. So, okay, so we see e to the x and cosine x. So then this will go to negative sine x, and then this goes to e to the x. So from there, we can plug in uv, which would be e to the x cosine x minus integral negative e to the, here, minus the integral of negative e to the x times sine x. This is just something I like to do when I see two negatives. I just turn them into positives. So after that, I think what we'll all see is we go through another iteration. U, du, v, dv. So we're going to have sine x, which goes to cosine x, e to the x, e to the x. So you're going to get e to the x cosine x, or excuse me, e to the x, yeah, sine x, as we said earlier. Cosine x, that's right, cosine x plus e to the x sine x minus the integral of e to the x cosine x. If everyone sees here, we're back to where we started. So our original formula, let me write it down again, was the integral of e to the x cosine x equals e to the x cosine x plus e to the x sine x minus the and then we have minus the integral of e to the x cosine x. So if we try to integrate this, you know, we're sort of stuck. It will just go over and over and over, and we'll see the same thing. But this is just sort of a little trick, and this is how you're supposed to solve this one. Is because we have e to the x cosine that's being subtracted, you shift that over to the other side, divide each of those terms by 2, and that's it, right there. This is one of the, you'll probably encounter one of these on a test. It's one of the trickier ones, but that's how you have to solve it, is you algebraically move that over to this side right here, and then you divide by 2. So you that's my presentation on integration by parts. If there are any questions, leave them in the comment bar and I'll get back to you.